Hello my beautiful PU2 aspirants. I know your exam is just after 2 days and few of you are thinking from where you should start, right? Maybe your pre-board examination was not so satisfied and that's why you are a little bit worried. Chemistry is very difficult to you, right? But this is not the time when you should think about it. Rather, you should focus on the most important question that can give you your satisfactory marks, right? So that's the reason I came up with the passing package. Here I assemble the sets of question that you should never leave before your examination. So these are the must do questions that you should go through before you are facing your examination. Yes, some additional boosters, everything will be there. I will come up with the live session. There we will discuss a lot of numerical problems, a lot of additional questions as well, MCQ as well. But these are the sets of questions that you must do. So yes, without further delay, let's get started. So see, as I already told you that you should not focus all the chapter as of now if you are not prepared well. Right? So where you should give your maximum focus? You should give your maximum focus to the high weighted chapter and comparatively easier chapter that can give you total 60 plus marks. Okay, let me tell you, in physical chemistry you have solution and chemical kinetics and electrochemistry. Comparatively easier chapter if you take solution and chemical kinetics. Okay. Now, coordination chemistry you take from inorganic rather than that of D and F block, okay? Then you can go ahead with the 3 easiest organic chapter, that is haloalkane, haloarenes, alcohols, phenols and ether, aldehyde, ketones and carboxylic acid. So these 3 chapters, here 2 chapters, here 1 chapters, right? Total 6 chapter, it can give you total 63 plus if you have prepared that very well. Okay, then you can boost up your marks by just doing a very small chapter, that is the amines. Okay, so this is the scheme you should follow up now if you are not really prepared well. Okay, but in my suggestion, go along with the chapter, go along with the sequence. It will give you quite a good marks. And if you are not prepared among the following chapter, D and F block, let's say biomolecule, electrochemistry, just go with the important questions, previous year question and model paper question from these chapters. I guess that's gonna help you. So yeah, let's get started. One more thing that I want to convey, if you are not prepared with any chapter, right now it's not a correct time to start with this. Don't go for it. Okay, don't start anything new. Okay, so yeah, first we will do solution, a must do chapter. See, a few 2-3 marker question I will discuss, very important question, you must do them. Okay, so state Henry's law and write its mathematical term. What is the significance of KH? So here you can see this is the Henry's law, that at constant temperature the solubility of gas in liquid is directly proportional to the partial pressure of the gas, right? And this is the formula, and definitely whenever you are writing the formula, what is P, what is KH, what is X, that you must denote. P is the partial pressure, I'm just writing in short. KH is the Henry's constant, let's write. P is the Henry's constant. X here, this is the mole fraction. This mole fraction, in the term of mole fraction only, the solubility is defined here. Okay, next, what is the significance of KH? That is higher the KH value, less the solubility. Okay, let's proceed with the next question. State Raoult's law and give its mathematical form. Okay, so here you can see this is the Raoult's law. It states that if you are having the mixture, I mean the solution of 2 volatile liquid, the partial pressure of each component of the solution is directly proportional to its mole fraction. Okay, so this is how we denote this. So P equals to basically P naught of A of XA, right? And similarly you will get another partial pressure with respect to second component. So PB, let's say partial pressure of B equals to P naught of B of XB. Now in accordance to Dalton's law we add them, but to that extent you should not proceed. Okay, you can stop it here with the like this particular formula. So my suggestion, whenever you are writing the formula or the mathematical terminology, make sure that you are mentioning what is what, means what is abbreviation, what is P naught of A. P naught of A means the vapor pressure of A at its pure state, right? So this type of things you have to mention. Next question, what is vapor pressure? So what is vapor pressure is basically, vapor pressure means any liquid, any volatile liquid if you take, let's say I am taking a bottle of water. In that bottle of water, just after the water surface to the cap, that entire space, is it completely empty? No, it's not completely empty. Vapor pressure occupied there. So what is vapor pressure? The water vapor that exerting the pressure on the container wall, that is called vapor pressure. Okay, so let me just write it for you. Number 2. So vapor pressure is the pressure exerted by the vapor present above the liquid when the system is in equilibrium. Okay, so this is what you can write out of it. Okay, so next question, if I proceed, the vapor pressure of CHCl3 and CH2Cl2 are given, that is 200 and 415 mm of Hg respectively. Which one is more volatile? So from here you can see that which is having more vapor pressure means that contains more vapor, means that is much volatile, right? So CH2Cl2 is going to be more volatile because vapor pressure coming out of it is maximum. Okay, let's go ahead with the next question. Write the expression to relate the cryoscopic constant and change in enthalpy of fusion. Explain the terms involved in it. Okay, so this is nothing but the expression that is related to the depression in freezing point. So let me just write it out. So basically if you write Kf, so Kf is called cryoscopic constant. Okay, so basically if you just write the delta Tf, so from delta Tf you will get it actually the Kf into m, right? So that Kf can be written as molecular weight into universal gas constant into Tf whole square divided by 1000 into enthalpy of fusion, Tf naught. Okay, so this is the expression for the Kf. Okay, now let me explain the terminologies. Here m is basically the molecular weight. Okay, R is the universal gas constant. Okay, Tf naught is basically the freezing point of pure solvent. Okay, and here delta H fusion is basically equals to enthalpy of fusion. Okay, so this is the relation. So in case of Kb, that is ebuloscopic constant. So this is cryoscopic constant. This Kb, it is basically ebuloscopic constant. Here the question is with respect to the cryoscopic constant. The same type of question you can expect with respect to the ebuloscopic constant as well. So that's going to be equals to same thing, m into R into here it will be TB naught, okay, whole square, divided by 1000 into enthalpy of vaporization. Okay, so this is the change. So I'm just writing TB naught here. So TB naught is the boiling point of the pure solvent. Okay, and this is basically enthalpy of vaporization. Okay, so these are the things that you have to remember. So you can expect the question in the any one of the form. Okay, so be prepared for both of them. I guess this is clear to you. Let's proceed for the next question. So here you can see, draw a graph to show the variation of vapor pressure of solvent and the solution with respect to temperature. Okay, so this is basically the elevation in boiling point. So here you can see initially vapor pressure and temperature graph we are putting. So this is for the solvent, this is for the solution. So you can see initially the delta T value was here, later on it becomes this. So delta T comes the elevation in boiling point. Okay, so I guess this is clear. Let me just write it down, which one is for the solvent, which one is for the solution. This is for the solvent and this is for the solution. Okay, so here you can see there are increase in boiling point. Okay, so I guess this is clear to you. It's one of the important question. Let's go ahead, give the difference between ideal and non-ideal solution. So I guess I don't have to explain this. You can write any 2 or 3 out of it, ideal and non-ideal solution. One obeys Raoult's law, another doesn't obey Raoult's law. With respect to delta H mix, delta V mix, you can go ahead, and the interaction between A and B component. Okay, let's go ahead and differentiate the types of non-ideal solution. Okay, so this is not the correct one. Wait. Okay, so differentiate between the types of non-ideal solution. So here you can see we can observe the positive and the negative deviation, right? So positive deviation, what happens? Total pressure is greater than P1x1 plus P2x2, and for this case total pressure is less than P1x1 plus P2x2. Delta H mix greater than 0, for that case less than 0. And for positive deviation, AB interaction is weaker than that of the individual AA and BB interaction. And for the negative deviation, if you go ahead, AB interaction is stronger. Okay, example you can go ahead with ethanol acetone, carbon disulfide and acetone. For negative deviation, you can go ahead with the phenol and aniline, chloroform and acetone, this type of thing. Okay, let's go ahead, differentiate between the maximum boiling azeotrope and minimum boiling azeotrope. So maximum boiling azeotrope, they shows negative deviation from the Raoult's law, and minimum boiling azeotrope, they shows positive deviation from the Raoult's law. And other difference that they boils at the higher temperature than that of the original boiling point of the each component. For minimum boiling azeotrope, they boil at the lower temperature. Okay, example you can write nitric acid and water. Okay, the percentage you must mention, because in this percentage only they will form the azeotrope. Okay, I guess it is clear. Let's go ahead. What is reverse osmosis? Give its application. So these are all theoretical questions, as you can see. So what is reverse osmosis? This basically whenever you are giving pressure more than that of the osmotic pressure, then what happened? From the high concentration zone, the solvent molecule passes to the lower concentration zone, right? So this particular process is called basically the reverse osmosis. So where it can be applied, it can be applied in desalination of water. Okay, so where we are doing that pressure we are giving almost 30 atmosphere. Okay, at around normal room temperature we are giving, and we can go ahead with the desalination. Okay, I guess this is clear to you. Okay, this is the process. You can see from the salt water, the solvent molecule comes to the freshwater zone. Okay, so let's go ahead. Okay, so basically here explanation of bends, anoxia and edema. Okay, so as you know, these three are the consequences of Henry's law. Consequences means these are the application part of the Henry's law. Okay, so what is bends? Bends basically that is a scuba diver that they fail when more nitrogen gets dissolved in the blood, right? That is called bends. And anoxia is what? Anoxia is less solubility of oxygen in the blood at higher altitude. As a result of this, you will feel nausea, you will feel dizziness, those type of thing, those symptoms, those are called nausea. Okay, edema. Edema is basically the water retention in the cells. Okay, so whenever you are you will just put your feet, usually in the feet, the older people, they used to they used to observe this edema when they put their feet into the hot water, that thing comes out. Okay, so I guess it is clear. Let's go ahead. Why the vapor pressure of solvent decreases on addition of a non-volatile solute? So basically what happens whenever you are having a volatile solvent, let's say you are having a volatile solvent. Okay, so now you are adding some non-volatile solute. So what happens, those solute, they gets accumulated at the surface area more. Okay, they get accumulated at the surface area of the non-volatile solvent. Okay, so as a result of this, what happens, the solvent being volatile, it will contribute maximum in the vapor pressure, but now the surface area gets accumulated, gets occupied by the non-volatile solute, and vaporization takes place from the surface area only. If the surface area is covered, then why the vapor pressure will come? It will not come definitely. That's the reason vapor pressure will be reduced. That is only the relative lowering of vapor pressure. Okay, so this entire explanation is giving here. I guess you will understand this. Let's go ahead. Okay, why the freezing point decreases on adding solute? Again the same reason. So basically whenever you are adding solute, non-volatile solute, then what happens, it gets accompanied, it gets accumulated on the surface area of the non-volatile, of the volatile solvent, right? The non-volatile solute gets accommodated on the volatile solvent surface area. As a result of this, the solvent molecule cannot escape from the surface. Okay, so as a result of this, what happens, vapor pressure decreases, and as a result of this, freezing point decreases as well. Okay, next, boiling point of solution increases on adding solute. The same reason, like when solute, non-volatile solute is added, the vapor pressure of the solution definitely decreases. Now the vapor pressure of the solution decreases. Now in order to make the solution boil, the vapor pressure of the solution must be increases, right? The vapor pressure of the solution must be increased by raising the temperature. If you give more temperature, then more amount of solvent molecule will come out. So in order to make the solution boil, you need to increase the vapor pressure. Okay, that's why you need more temperature. Okay, that as a result of this, boiling point of the solution increases. I guess this is clear. So this is the graph. Okay, let's go ahead. This is a graph for both, one for the freezing point, another one for the boiling point. Okay, so this is for the freezing point, this is for the boiling point. Okay, let's go ahead. Okay, so one numerical problem, you can see 1 gram of okay, the problem is 1 gram of a non-electrolyte solute dissolved in 50 gram of benzene lowered the freezing point of benzene by 0.40 Kelvin. The freezing point depression constant of benzene is 5.12 Kelvin kg mole per liter. Okay, the molar mass of the solute, you have to calculate. So you can directly go ahead with the delta TF formula. So let me just do it for you. So what are the given thing that you have to focus at first? W2 is given, right? That is 1 gram of benzene. Okay, one more thing, W1 is also given, that is 50 gram of benzene. Okay, 1 gram of non-volatile liquid, this is the solute portion, and 5 gram of benzene, that is the solvent. Okay, now delta TF is also given, that is basically how much increase? 0.40 Kelvin. Okay, now let's put the formula. Delta TF is basically equals to KF into molality. So now let's write down the formula of molality, that is W2 by M2 into 1000 divided by W1. Next, substitute the things. Here 5.12, here I will get how much? 1 divided by molecular weight. Molecular weight you can write, you have to find out molecular weight, right? Here 1000 divided by, here it is 50, right? Okay, so I guess this is clear. This is 50 gram. Okay, and delta F value you can write, that is 0.4. So from here, if you just find out this M2, then like if you just calculate the value of M2, you will get your answer. So I'm not going for the calculation. So you can see the answer will come up to be 256 gram per mole. I guess you understood. Just write down the formula. Okay, please make sure you are going through all the formula properly, because this formula, writing the correct formula will give you 1 mark. Okay, substitution will give you another 1 mark. Okay, and this answer along with the unit, it will give you another 1 mark. Okay, so make sure you are going through the formula properly and you are substituting the value properly. Okay, let's go ahead with the next problem. It is a very important problem actually. I'm just writing as VVI. Okay, the boiling point of the benzene is 353.23 Kelvin when 1.80 gram of a non-volatile, non-ionizable solute was dissolved in 90 gram of benzene. The boiling point raised to 354.11. Calculate the molar mass of the solute. Okay, so let's go ahead with the problem. So initially the boiling point was, means TB naught. TB naught was something like 353.23 Kelvin, right? Yes. Next, TB means after the solute was added, it was increased to 354.11 Kelvin, right? Now another thing, what is given? W2. W2 means weight of the solute. W2 is given as 1.8 gram. W1 is also given, weight of the solvent, that is how much? 90 gram of benzene. Okay, so Kb also given. You can see Kb value is given 2.53. 2.53. Okay, let's go ahead. So now we will proceed with the formula, that is delta TB. So delta TB is basically equals to Kb into molality formula. Molality formula you know, W2 by M2 into 1000 divided by W1. Now delta TB we can break down in the form of TB minus TB naught. Okay, minus, that is equals to Kb equals to W2 by M2 into 1000 divided by W1. Okay, so now what you have to do, just substitute, that is 354.11 minus 353.23 equals to Kb value you know, that is 2.53 into 1.8, M2 we have to find out, into 1000 divided by 90. So if you just find this out, if you just find this out, then M2 if you have to calculate, I am not going for the calculation, so you will get the value 57.27, okay, gram per mole. Okay, so this is kind of the thing that you have to go through, and calculation part I guess you can do it. Okay, let's go through the next problem. Calculate the osmotic pressure in Pascal exerted by a solution prepared by dissolving 1 gram of polymer of molar mass 185,000, okay, in 450 ml of water in 370 degrees Celsius. Okay, so this is also one of the very important problem. Okay, don't skip this type of problems. Okay, so first, as usual, you have to write down whatever the informations are given out it. Okay, so W2 is going to be 1 gram. Okay, M2 is given, you can see the big one, 185,000. Okay, volume is given 450 ml. T is given as 370, right? It is given as 370. 370 means 643 Kelvin. Okay, so now we know pi equals to CRT. Okay, so C can be written as W2 by M2 into 1000 divided by volume, right, into R into T. Now you just have to substitute the value, that is 1 gram divided by 185,000 gram per mole, okay, into 1000 divided by volume is 450 ml into here unit you need to write, that is in the liter atmosphere, right? Okay, because here all together it will come up to be liter. Okay, so here this will come up to be liter. So as usual, you have to write the R in the liter atmosphere unit. So that's gonna be 0.083 liter atmosphere mole inverse Kelvin inverse, right, into 643 Kelvin. So everything will be cancelled out. Here you can see gram will be cancelled out. Okay, here liter will be cancelled out. Kelvin will be cancelled out. So you can calculate the answer. So you can see your answer will be something 30 point. Okay, that is in the Pascal. Fine. Let me just tell you something. If you just calculate, the answer should come in atmosphere here. Okay, whatever the calculation part, it will come in atmosphere. Okay, so if you want to find out the unit in the Pascal, because they have mentioned already, you have to find out in Pascal, just multiply with 10 power 5. So the answer into 10 power 5, that will give you the unit in Pascal. Okay, so your answer will come up to be 30.9. So the calculation part I am avoiding here, just normal calculation, just go through it. Whatever the answer will come, it will come in accordance to the atmosphere. Okay, every unit will be cancelled out. You can see everything here, mole will be cancelled out. Okay, so atmosphere, from atmosphere to Pascal, you have to just multiply with 10 power 5. Okay, I guess this is clear. Let's go ahead. Okay, let's go ahead with the next problem. Here you can see the question, vapor pressure of benzene is given, that is 200 mm of Hg. Okay, let's write one by one. Vapor pressure of benzene means P naught of benzene, it's given as 200 mm of Hg. Okay, so now next, when 2 gram of the non-volatile solute, so like given mass of the non-volatile solute is 2 gram, is dissolved in 78 gram of benzene. Benzene has vapor pressure of 195 mm of Hg. Okay, so from their pressure of the solution, it becomes 195 mm of Hg. We can see the relative lowering of vapor pressure. Initially pure benzene was 200. After being added with the solute, it reduced to 195. Right? Okay. Calculate the molar mass of the solute. Okay, fine. Let's go ahead with the problem. So if I just put the formula, okay, so W2 is given as 2 gram, that is also that also needs to be written, and W1, that is the weight of the solvent, that is also given 78 gram. Fine. Okay, now if I just write the formula, that is relative lowering of vapor pressure, delta P by P naught is basically mole fraction of solute, right? So if I just break it down, P naught minus P divided by P naught is going to be mole fraction of B. So mole fraction of B can be taken as number of moles of B divided by number of moles of A plus B, number of moles of A plus number of moles of B, right? But here what we are going to take, see here number of moles of B is going to be really less compared to that of the number of moles of A. If I just calculate, you will understand. Number of moles of A, it's going to be 78 gram given weight divided by 78 gram, that is basically going to be 1 mole. Okay, and NB, okay, NB you can see 2 gram, okay, 2 gram is given, and let's say M2, that is a molecular weight of the solute, that we don't know. Okay, this is really small compared to that of the A, right? So from there we can take it as NB divided by NA simply. Okay, so finally if I just put all of them together, it is coming up to be something P naught minus P divided by P naught is equals to NB by Na. Okay, now what you have to do, simply you have to substitute. So P naught is something 200 minus 195, right, divided by here you are getting 200, right? Here NB I can simply write it as 2 by M2 divided by 1. Okay, so now it's a simple calculation. If I just continue, here I am getting 5 by 200, here I am getting 2 by molecular weight, right? So from here M2 if I calculate, it's going to be 2 into 200 divided by 5, right? So if you just calculate this thing, 40, 42 is 80, so 80 gram per mole, that is the molecular weight. Okay, I guess you understood this. Yeah, 80 gram per mole, that is going to be the answer. Okay, I guess this is clear to you. So all the colligative property in accordance to the Van 't Hoff factor you have to remember properly. Okay, so here you can see one terminology is used here. Vapor pressure of benzene, here you can see 2 gram of a non-volatile solute. Okay, non-volatile, okay, leave it. I guess it is clear to you. Okay, I guess this is clear to you. Let's go ahead. Okay, so here we are going to start the chemical kinetics chapter. First question you can see, what is pseudo first order reaction? Give example. So I guess you remember the particular definition. So it's a higher order reaction can be converted into the first order reaction. Okay, when one reactant is present in excess. Okay, so that is basically the pseudo first order reaction. You can give the example of the acid hydrolysis of the methyl acetate. Okay, means hydrolysis of any ester you can take basically. Okay, and another one example you can go ahead with the inversion of the cane sugar. Okay, so I guess it is clear to you. Let's go ahead. Collision theory, one question you can expect out there. What are the main criteria for the effective collision according to the simple collision theory? So you can take the example of activation energy, it's one of the most important, and the proper orientation of the molecule, that's also very much important. Okay, so activation energy, proper orientation of the molecule, and one more thing you can just take into account, that is the effective collision. Okay, so I guess it is clear to you. Let's go ahead. Explain the effect of catalyst on the rate of the reaction. So this is the entire thing you can see, if reactant and this is the product, initially in absence of the catalyst it will take this much amount of activation energy, but in presence of catalyst it will take this much. So you can see it reduces down the activation energy, it decreases the activation energy by providing new reaction path. Okay, so I guess it's clear. Let's go ahead. This is the difference between order and molecularity. Okay, so here whenever it comes to the order and molecularity, it's a differentiation, this type of question whenever you have to like distinguish in between two. So for those cases these are something can give you the full marks. Okay, so all this type of question like the difference between order and molecularity, and the solution chapter also we had been through ideal, non-ideal solution, okay, positive deviation, negative deviation, okay, and maximum boiling azeotrope, minimum boiling azeotrope. So please make sure that you are going through all this question, because here there are no chance to cut your marks. Okay, so these are the differences in between them. So just take any 4 or 5 out of it as per the question mentioned, and you can just go ahead with the question. I guess this is clear. Next, write the Arrhenius equation, state as to what the symbol stands for. Okay, so this is the Arrhenius constant. You can see K equals to A into e power minus EA by RT. So K is a rate constant here, A is the frequency factor, okay, E is the exponential, EA is basically activation energy, R is the universal gas constant, and T is the absolute temperature. I guess no doubt here. Next, explain Arrhenius theory of activated complex by using the potential energy diagram. Okay, so basically what happens when the reaction takes place, the reactant molecule, they collide. Let's say H2 and I2, they are reacting, they will collide, and if they reaches activation energy, here they will form the activated complex. So activated complex is something, it's neither the reactant nor the product. So here you can see it's an intermediate that it forms. Hydrogen is also having the bond with another hydrogen, and hydrogen is also made another bond with iodine as well. Okay, so this is intermediate complex, that is only the activated complex, and that is formed here in the transition state. Okay, so once the activated complex is formed, then from there the product formation is the easiest. Okay, so this is basically the activated complex theory. Okay, I guess you understood. So this particular energy diagram you have to explain over there. Let's go ahead. Okay, let's go ahead with the next problem. Here you can see using the energy distribution curve showing the temperature dependence of the rate of the reaction, explain the effect of temperature. So this is in accordance to the Maxwell-Boltzmann distribution. So here you can see initially, let's say if the temperature is this T, so now it is covering this much area. So this area basically represent the fraction of molecule that has the energy more than that of the threshold energy. They will only give you the product. Okay, now if you increase the temperature by 10 degree more, T plus 10, now you can see it has covered more area, right? Means more fraction of molecule will take part in the reaction. Okay, so I guess you understand, as you are just increasing the temperature, what happens? More number of molecules will cover the threshold energy and they will give you the product. Okay, I guess it's clear. Let's go ahead. Name the factors affecting the rate of reaction, or on which factors does the rate of a reaction depends. Okay, so basically there are few factors that you can just name in the examination copy, like the nature of the reactants, temperature, catalyst, concentration, presence of light sometimes. Okay, this type of example you can take. Okay, let's go ahead, derive an expression for integrated rate equation for zero order reaction. Okay, let's go ahead, it's a very important. Okay, and this type of question make sure you are going through, because it will come up to be a 3-marker question. Okay, and if you do the proper derivation, then you can confirm that 3 marks will come. Okay, so here you can see, you can start with a simple reaction, that reactant is giving product. Okay, from there rate equation you can write. See, this is the differential rate equation, you can write minus dr by dt into k, and here in accordance to rate law you can write k into r power 0, because it is a zero order reaction, so r power 0 is 1, so rate equals to k. Now equate them. So on being like equated, it will come up to be just little bit, if you do rearrangement, then this dt will come up to be here, right? So minus dr by dt equals to k. So here you just multiply the dt here. Okay, so you will get dr equals to minus k into dt. Now you integrate. Okay, so on being integrated, you will get I, that is an integration constant. Okay, so now what you have to put? You have to find out the value of I, right? So in order to find out the value of I, T you can put it as 0, R you can put it as R naught. Okay, so your I value will come up to be R naught. So now put it into the final equation. Okay, so Kt plus R naught. So now on being rearranged, it will give you K equals to R naught minus R by T, or you can like proceed like this as well, or you can go through the way I discussed in the last videos itself, that you can take the limit when T equals to T naught, R equals to R naught. You can directly put the limit in the integration itself, that will give you the direct result. Okay, I guess it's clear. Let's go ahead. Okay, so derive an expression of half-life period of zero order reaction, or show that zero order reaction half-life period directly proportional to the initial concentration. So here you can see this is the zero order rate equation just now we discussed. Okay, so now whenever half-life means half reaction is over, means T equals to T half, then reactant will be R naught by 2 initial divided by 2, right? So now substitute the value in the main equation. Okay, so that will give you K equals to R naught by 2 into T half. So from there T half equals to R naught by 2K. Okay, from there you can tell that the T half is directly proportional to that of the R naught, that is the initial concentration. So I guess this is clear to you. Let's go ahead. Okay, derive integrated rate law for the first order reaction. So here you can see this is a first order reaction. In the same way I am taking a simple reaction, reactant to product. Next, with respect to rate law, rate equals to K into R power 1, and with respect to differential rate equation you can see minus dr by dt. Now equating two of them, minus dr by dt equals to K into R, integrate it, you will get I. Calculate the I from this, substitute T equals to 0 and R equals to R naught, you will get I value. Okay, now what you have to do, you just have to substitute the value of I in the main equation here. Here you have to substitute the value, sorry. Here you have to substitute the value, right? So now once you substitute and on being rearranged, you can get this equation. After that, from the ln you can convert this into the log, that you have to multiply with 2.303. Okay, so you will get K equals to 2.303 by T log R naught by R. I guess it's clear. Let's go ahead. Okay, so here you can see, show for the first order reaction half-life period is independent of the initial concentration. So here you can see again in the same equation I will take R naught similar, and R I will take R naught by 2, because I am taking T half. In T half initial reactant it will be half of it, right? So R naught by 2, let's put it here, and on being calculated it will give you T half equals to 0.693 by K. You can see there is no term of concentration, right? So you can see that the half-life of the first order reaction is independent upon the first order reaction. I mean the concentration of the initial concentration of the reaction. I guess it is clear to you. Let's go ahead. Okay, let's go ahead. So here you can see, let me just take a very simple reaction. Let's A is giving you B plus C. All of them are in the gaseous phase. Okay, this is also gaseous. Okay, this is also gaseous. We have to deal with the reactant only. Okay, so now here you can see the pressure of A. If I just write it, let's say whenever T equals to 0 means initial state. Okay, so pressure of A, let it be P initial, Pi. Okay, this is 0, this is 0. Okay, when T equals to T at a certain time, okay, let's say some amount of B and C will be formed. So let it be X, that is the pressure of B and C at time T. So what will be the pressure of A? It will be Pi minus X. Okay, I guess this is clear. Up to this it is clear. Now if I find out total pressure at time T, at this time what is the total pressure coming out from the reactant? Unreacted reactant means this and this. Okay, so let it be PT. So it will be this plus this plus this, right? So Pi minus X plus X plus X. So I am getting Pi plus X, right? This is my PT. And what is X here? X is basically PT minus means total pressure minus the initial reactant pressure, that is the X value. Okay, I guess up to this it is clear. Now what you have to do? Now if I find out pressure of A at time t, that's going to be Pi minus X. Let's put the value of X here. Pi minus Pt plus Pi, right? So from here you are getting 2 Pi minus Pt. Fine, I guess here is no doubt. Now we will put all these value together in the first order equation. Okay, so that's going to be K equals to 2.303 divided by T into log P naught of A by PA, right? So let's put the things here. So it's going to be K equals to 2.303 divided by T. It's going to be log P naught of A, we can take it as Pi, initial pressure, divided by PA, we can take it as 2 Pi minus Pt. Okay, so here what is P naught A? That is the initial pressure of A. Okay, and what is PA? PA is the pressure of A at time t. Okay, so this is the equation in the gas phase. Okay, I guess you understood. Okay, so from where do we have to start? We have to start with the gaseous phase equation, where the reactant is gaseous. You can take it as A, like this is the gaseous. Whenever T equals to 0 means initial state, the pressure of A is Pi. For them it's not yet prepared, so 0 0. Now whenever T equals to T at a certain time, then it will be, let's say the pressure of B, let it be X, pressure of C, let it be X. Okay, so here the pressure becomes Pi minus X. Okay, so now total pressure at time t, it's going to be this, because in my particular container of the solution, not solution, in that particular reaction container, I am having unreacted A plus B plus C. So add them, Pi minus X plus X plus X, that will give you Pi plus X. Now what is the value of X? X is the basically the pressure of the product, right? So that is basically total pressure minus Pi. Okay, from here I can get, see, Pt is basically Pi plus X. So X will be equals to, from here X will be equals to Pt minus Pi, right? So now pressure of A, that is Pa basically, that is nothing but the Pa at time t, means this one, Pi minus X. Put the value of X here, Pt minus Pi. Okay, from here I am getting 2 Pi minus Pt. Okay, now you have to put all this value into the first order rate equation, integrated rate equation. So here you can see it should be Pa naught by Pa. Okay, so here if you just put the Pa naught value, that is nothing but Pi divided by 2 Pi minus Pt. I guess this is clear to you. Let's go ahead with the next problem. Okay, calculate the time in seconds for the decomposition of nitrogen pentoxide which follows the first order kinetics when concentration of N2O5 is dropped from 0.1 to 0.01 molar. Okay, so that's basically, you just have to go ahead with the first order rate equation, integrated rate equation. Okay, so from there I can write T is basically equals to 2.303 divided by K, right, divided by K into log of initial concentration of N2O5. So N2O5 0, let's write, and this is the concentration of N2O5 at time t. Okay, everything is given here, 2.303, K value is also given, that is 6.22 into 10 power minus 4 second inverse, log, here concentration term it should be 0.1, right? Initially it was 0.1. So let's write it as 10 power minus 1 divided by 10 power minus 2. Okay, so this is the thing. If you calculate this entire thing, you will get the answer for T. Okay, so you can see the answer should come up to be 3.7 into 10 cube second. I guess it is clear to you. Let's go ahead. Okay, the question is, the graph of log K versus 1 by T for a reaction is linear with intercept of 10 and slope of minus 5.1 into 10 cube. Okay, calculate the frequency factor and EA for the reaction. Okay, fine, you have to use the Arrhenius equation here. Okay, so what is the equation? Log K equals to log A minus EA by 2.303 R into 1 by T into 1 by T. So if you just look at this equation, this particular thing is going to be your Y, right? This log A is going to be your C, right? That is the intercept. Okay, this minus EA by 2.303 into R is going to be your M, and 1 by T is going to be your X. So the graph will be log K versus 1 by T. Okay, so intercept is given, means log A value is given. Log A is basically 10. Okay, from there you can get A equals to 10 power 10. So that is the value of your A. Okay, the frequency factor. And if I want to calculate the EA, okay, so I can take the slope value as well. 5 into EA by 2.303 into R, that's going to be 5.1 into 10 cube, right? So you can calculate the EA from here. Okay, 2.303 into 8.314 into 5.1 into 10 cube. You will get the value of activation energy as well. Okay, so here is the answer. You can see first A value will come as 10 power 10. Okay, that's it. And EA, if you just multiply this thing, you will get it. Okay, I guess it's clear to you. Let's go ahead. Okay, the rate constant of a reaction at 500 Kelvin and 600 Kelvin is given respectively. Calculate the energy of activation. So this is also following the Arrhenius equation. Okay, important question. So let's go ahead. Formula is basically log K1 by K2 is basically equals to EA by 2.303 R into T1 into T2, T2 minus T1, right? So substitute the value here, log 0.07 divided by 0.02, okay, equals to EA. You have to find out 2.303 into 8.314. Here is going to be 700 minus 500 divided by 500 into 700. That's it. So from here, if you just calculate the EA, you will get your answer. Okay, so you can see your answer should come up to be something like 18.228. Okay, I'm just showing the original formula and how you should substitute the things. The calculation part you should go ahead. Okay, next you can see, following the data obtained for the reaction A plus B gives P. What is the order of the reaction with respect to A and B? Write the rate law. What is the rate constant? What is the half-life of the reaction? Okay, let's go one by one. So if you just normally write rate equation, it's going to be K into A power X into B power Y. So you just have to find out the value of X and Y. Okay, so what basically you have to do, you have to arrange this data in such a way so that you can get the value of X and Y. Okay, arrange the data means, see, if I simply do, let's say 3 divided by 1, I'm showing you. So from here I am getting 4 into 10 power minus 3, that is the rate value, divided by 1, it is 2 into 10 power minus 3 equals to, that's going to be K into 0.4 power x into 0.3 power y, right, divided by k into a value you can see here 0.2 power x, and here you are getting 0.3 power y. Okay, at least one term should be cancelled out. Okay, so here you can see I am getting 2 equals to, here also I am getting 2 power x, from there I am getting x equals to 1. Okay, similarly if you just go ahead with 2 divided by 1 or 1 divided by 2, I can go ahead. Okay, 1 divided by 2. Okay, 1 divided by 2. So for this case I will get it as 2 into 10 power minus 3, here also 2 into 10 power minus 3, here you can see k into 0.2 power x into 0.3 power y. Okay, here also k into 0.2 power x into 0.1 power y. Okay, so from here see I am getting 1 and here I am getting 3 power y. So something power 0 only can be y, from there I can get y equals to 0. So my equation becomes, so one by one let's write. Okay, what is the order with respect to a? With respect to a the order is coming as 1. With respect to b the order is coming as 0. Write the rate equation. Rate equation is going to be r into k a power 1 b power 0. Okay, I guess this is clear. Let's find out, okay, let's find out the rate constant. Okay, let me just do it here. So basically what you have to do, see this reaction is 0 order with respect to b. So my final equation is becoming something like r equals to k into a, right, because b power 0, right. So from here I can get k equals to r by a, right. So r value if I write, any one value you can take, let's say I am taking this one, 2 into 10 power minus 3 divided by concentration of a, you can see 0.2. So from here you will get 10 power minus 2. So constant rate constant value is coming up to be 10 power minus 2. Okay, so definitely it's going to be second inverse. Okay, next what is the half-life of the reaction? So let me do the half-life here. So T half, what is the formula of T half? T half is basically 0.693 divided by K. So 0.693 divided by K value you know now, 10 power minus 2. So from there I can get the half-life as 69.3. Okay, I guess this is clear to you. Okay, let's go ahead. In a chemical reaction, A plus B gives C plus D. The concentration of the reactant A alone is increased by 2 times. The reaction increased by 4 times. If the concentration, okay, one by one let's write. Again it is the initial rate method. So R equals to K into A power X into B power Y. Okay, what they are saying, if the concentration of A is doubled, right, then the rate is increased by 4 times, it will be 4R, right. This is my equation 1, this is my equation 2. Okay, now if the rate is increased by 4 times, okay, if the concentration of both A and B increased, now what we will do, K into 2 into A power X, 2 into B power Y. If I do, then rate is increased by 8 times. This is my equation 3. So what I am going to do is equation 3 by 2 I can go ahead. Okay, so 8R equals to K into 2A power. Okay, so what we can do is equation 3 divided by 2. So if I do this, 8R is basically equals to K into 2A power X 2B power Y divided by, here I will get 4R and here divided by k into 2a power x into b power y, right? So from here what I can do is I will get 2 here, here everything will be cancelled out, and here you will get 2 power y. So from here you can see y value you are getting as 1, right? So now what you can do, okay, let's do 2 divided by 1. Let's do 2 divided by 1. So equation 2 is something 4r divided by r is going to be k into 2a power x into b power y, okay, divided by k into a power x into b power y. So from here I am getting 4 equals to 2 power x. From there x value is coming up to be 2, okay. So what is the order of the reaction with respect to A and B? So with respect to A the order is going to be 2, and with respect to B the order is going to be 1. If I write the rate equation, it's going to be something like A power 2 into B power 1, okay. I guess this is clear to you. Initial rate method, important problem, okay. Let's go ahead. Okay, so we are going to start with the coordination compounds. Okay, so let's go ahead with the coordination compound chapter. So first question, explain with 2 examples the following, that is the chelating ligands, homoleptic, heteroleptic and ambidentate ligand. Fine. So these are the examples. You can see when a di or polydentate ligand uses its 2 or more donor atoms simultaneously and it binds a single metal ion, okay, it's called as chelating, okay. So one example you can take it as EDTA, sorry, one example you can take it as EDTA. Okay, next homoleptic complex. Homoleptic complex means in the coordination sphere only one type of ligand will be there. Okay, you can see in the coordination sphere nickel is bound with only one ligand. Okay, one type of ligand. Okay, heteroleptic complex is like when central atom is coordinated with different type of ligand. Okay, here you can see nickel is coordinated with chlorine as well as water. This is an example. Next, ambidentate ligand, right? It's very important actually, ambidentate one. It's very important. A molecule or an ion which has 2 donor atom to form 2 coordinate bond with the central metal, but this particular case, whenever it is an ambidentate ligand, it donates from a single end. Okay, so wait, this is not the definition properly. So ambidentate ligand, you can write it as, just a minute, a ligand has 2 donor site or 2 donor atom, better to say 2 donor atom, but either of them bind to the metal at a time. Okay, let's take one example as Cn minus. It has 2 donor side, both the carbon and nitrogen. Okay, either from the carbon end it will bind or from the nitrogen end it will bind. Okay, let's go ahead. Okay, draw the isomers of PtCl2En2 and COEN3. Okay, so for this case we will get cis and trans. Okay, and cis will give you the optical isomers. Let's draw it one by one. So for the first case, let's draw the trans at first. Wait. So this is your trans isomer. Okay, so if I draw the cis, it will be something like this. This is your cis, right? So for this case, you can see there are no symmetry element that are passing through it. So you will get one optical isomer, means enantiomers out of it. Let's, if it is D, you will get the L. So just draw the mirror image of it. So let it be your L. Okay. So this is for the first one. Next one you can see. Next one is also an, you will get the optical isomer out of it. You will get the enantiomer. So let me draw it. So for this, if I just draw the mirror image, you will get it something like this. Okay, I guess there is no doubt. Let's go ahead. Okay, out of the following two coordination entities, which is chirally active? So definitely this cis, this particular version is going to be optically active. Okay, next draw the structures of its enantiomer. Okay, let's draw it. So chromium in the middle. Okay, oxalate, right? So this is a bidentate ligand. So you can show the bond like that. Here chlorine. Okay, so it is a cis isomer. So let's draw the mirror image of it. Chromium. This is oxalate. Here also Cl, here also Cl. If one is D, another one is L. Okay, I guess this is clear to you. Let's go ahead. Okay, state the postulates of Warner's coordination theory. So this is basically the theory. You can just talk about the primary and secondary valency, okay, and how they are satisfied, one by the ligand, another one by the ions, okay, and how they are spatially oriented. Okay, how the ligands are spatially oriented, that particular idea also you will get out of it, means the spatial arrangements. Okay, so I guess this is clear. You can just take the points from here and you can go ahead. Next, okay, first explain the ionization isomerism with example and explain the linkage isomer. So here comes the examples. You can see linkage isomer it arises because of the ambidentate ligand present in it. So for this case, let me just write the isomer NH3 it should be ONO then Cl2. Okay, this is the another isomer of it. So here you can see ions that it will dissociate. Okay, so those two ions will be different. Okay, here for this case you will get Br minus, here you will get SO4 2 minus. Okay, let's go ahead. Okay, coordination isomerism and solvation isomerism. So here you can see coordination isomerism, just the ligand will be exchanged, interchanging, okay, here. And for this case, solvation means the amount of water, okay, inside the coordination sphere and outside the coordination sphere will be different. Inside the coordination sphere means directly bound with the metal, okay, and outside means it's a counterpart. Okay, so you can see the color also becomes different. Let's go through. Okay, draw the isomers of this species. Okay. Okay, let's go ahead with the next question. Draw the isomers of this species. So for these species, it is a MA3B3 type of complex, right? So you will get two type of isomer. One is facial, another one is meridional. Okay, let me draw them. Okay, so here you can see, if you just connect this thing, this is your facial. Okay, if I'm just showing you by connecting them. This is one of the plane, and another one plane you can see, it's like that. So see, these two planes are facing each other, right? So it's going to be facial. Okay, now another isomer, the planes will cut each other, right? So you can draw it like CO. Okay, so for these case you can see, if you just connect the plane, they will cut each other. Okay, so for this case the plane will be something like, wait, so this is one plane and another one plane is like that. So you can see they are perpendicular to each other, right? So this is going to be meridional. Okay, so I made a proper video like while explaining these things, like not a proper video like previous live session I have taken on this, because there I have discussed top 50 question. Okay, there I explained well about the facial and meridional, how they arises. Okay, one of the question you can expect out of that, if you don't know the concept, you can go and watch the live session. Okay, there you will get the proper clarification out of it. Okay, next, hybridization, magnetic property and geometrical and geometry of this particular species. Okay, let's go ahead with it. So I am having cobalt, right? So cobalt 3+, cobalt 3+ means I am having D6 system. Okay, so if I just write D6, this is my 3D, this is my 4S, this is my 4P. Okay, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. Okay, now whenever cobalt 3+ is in excited state, what happens? Because see, this is a strong field ligand. Okay, it's a strong field ligand, so it will insist the lone pairs to be paired up against the Hund's rule. Okay, so this will go here, this will come here. So as a result of this, it will get the 3D configuration something like this. 1, 2, 3, 4, 5. Okay, and 2d orbital will be empty. This is your 4s, this is your 4p. Okay, as a result of this, this 2d empty d orbital, 1s and 3p, they will make D2sp3. Okay, D2sp3 hybridization. Okay, here D2sp3, if you see, 2d orbital, 1s orbital and 3p orbital. Okay, here the ammonia will make the bond. Okay, here 6 ammonia will create the bond. Okay, so D2sp3, so shape is going to be, or geometry is going to be octahedral. Okay, and as you can see, there is no unpaired electron, right? No unpaired electron, hence you can get diamagnetic character. Okay, I guess this is clear to you. Let's go ahead. Okay, so this is the application part. From the application of the coordination chemistry also you can get some questions. So just go through this. This can be of help to you. Okay, so let's go ahead. Here comes the question, synergic bond in metal carbonyls. Okay, so what is basically synergic bond? So basically first what happens, the metal carbon bond in carbonyls, it possesses both S and P character. So first what happens, metal carbonyl sigma bond is formed, from where the carbon actually donates the lone pair to the metal vacant d orbital. Okay, so then what happens, metal gets saturated with electron, so it gives the electron cloud again back to the carbonyl. So carbonyl takes up the excess electron from the metal to its anti-bonding pi star orbital. Okay, as a result of this back bonding, the P character arises. Okay, this is called synergic bonding. Okay, as you can see, both sigma and pi character, it's a very strong type of bond. Okay, I guess this is clear. Let's go ahead. Limitation of CFT and limitation of VBT. Okay, first limitation of VBT, you can see it does not give any quantitative interpretation about the magnetic data. Next, like one example for this case, you can see in accordance to the VBT, oxygen will be diamagnetic, but in nature oxygen exists in paramagnetic. Okay, so that particular information you will get if you further proceed with the molecular orbital theory. Okay, next you can see the color cannot be explained. Next, like kinetic stability, thermodynamic or kinetic stability of the coordination compound cannot be explained. Next, exact prediction regarding the tetrahedral or square planar structure, that also cannot be explained. Okay, it does not distinguish between the weak and strong field ligand as well. Next, here you can see limitation of CFT. CFT actually they consider the metal and ligand as a point charge. This is one of the thing, and they always account, they does not account the covalent character of bonding between the metal and ligand. They always like go ahead with the electrostatic interaction in between the metal and ligand. Okay, the covalent character is neglected here. So these are the limitation of CFT. Okay, so crystal field splitting in octahedral, you can see here what happens, basically metal and ligand, right? So whenever the ligand approaches to the metal center, right, then what happens, the electron ligand has its own electron sphere, metal is also having its own electron sphere. The repulsion between the electron sphere takes place. As a result of this, 3 orbitals of the M for the metal, they becomes lower energy, and 2 becomes higher energy. 3, they are called togetherly as T2G, that is dxy, dyz and dzx, and 2 gets maximum energy because they faces maximum repulsion. Okay, that is dx square minus y square and dz square. From the middle, this is called the barycenter. Above barycenter, the energy gap is 3/5 del O, and below barycenter it is called 2/5 del O. The total energy gap is called delta O, means crystal field splitting energy. So this is what you have to explain over here. It's a very important question. Okay. Okay, next here you can see, draw the figure, show the splitting in the tetrahedral. So tetrahedral and octahedral, be careful about it. All the things are similar. Just remember the 2 orbital that was up, energetically up in the octahedral, in tetrahedral they become down. Okay, means dx square, y square and dz square will be coming down, and they are called as E, not Eg, it's E only. And 3 orbital, they will be of high energy, they are called as T2. So the energy gap will be changed as well. So middle, it is the barycenter, and delta T is called as tetrahedral crystal field splitting energy. Okay, next here you can see above barycenter 2/5 del T, below 3/5 del T. I guess it's clear to you. Let's go ahead. Okay, let's go ahead with the D and F block. Okay, so let's go ahead with the next question. Calculate the magnetic moment of SC3 plus, calculate the magnetic moment of 3I3 plus. Okay, any one I am doing here. Let's go ahead with the Ti3 plus. Okay, so if you see Ti3 plus is a 3D1 system, right? So Now you can see all the question, whatever the type here, calculate the magnetic moment of a divalent ion in aqueous solution when the atomic number is 25. Okay, so these type of question can be answered in the similar way. You can use the same formula. Okay, so here I can use, see, only one unpaired electron is present, so magnetic moment can be explained with n into n plus 1, right? So here you can see 1 into 1 plus 1, so you will get root 2, that's going to be 1.414, I guess, Bohr magneton. Okay, that's it. So using this formula you can go ahead with the calculation of the magnetic moment. Okay, spin only magnetic moment. So let's go ahead, explain the formation of interstitial compounds. So interstitial compounds are formed when the small atoms like carbon, nitrogen, hydrogen, they get trapped, okay, inside the cavities of the lattice of metals. Okay, so you can see Mn4C, Fe3H, these are the interstitial compounds. Okay, so some properties you can see, the physical and chemical properties of the compounds, they have very high melting points, they are chemically inert, and they retain the metallic conductivity. Okay, so these are the properties. Next, explain the catalytic property of the transition metal. So transition metal shows the catalytic activity just because of the variable oxidation state. Okay, another option you can take it as the absorption area. Area of absorption is very large for them. Okay, next, incompletely or partially filled d orbital they are having. Okay, next, intermediate compound formation they makes easier. Okay, like you can see one example is also given here for the catalytic process, like vanadium pentoxide, it is used for the contact process for the manufacture of H2SO4. Clear, I guess? Let's go ahead. It's a very important question, okay? This particular question is very important for this year. Next, what is the composition of the mixed metal? So this particular question I guess you got in your pre-board examination, so be careful, it is also an important one. So basically lanthanoid should be 95% and traces of iron should be less than or similar to that of the 5%, or some trace of sulfur, carbon, calcium or aluminium. Okay, so this particular composition is called mixed metal. Okay, it can be used in magnesium based alloy to produce bullets, okay, shell and lighter flint, etc. Let's go ahead. Why cerium shows +4 oxidation state, and what is the highest oxidation state? What is the highest oxidation state shown by actinoids, or name an element that shows the highest oxidation number among the actinoids? Both of them are very important. Okay, so basically cerium shows +4 oxidation because it will get the inert gas like configuration, that is xenon. 4F4 system, only Xc. If it forms cerium 4, if it forms cerium 4 plus, then it will be 4F0, right? Sorry, it is basically 4F3 3D1, right? 5D1, sorry, 4F1, so 4F3 3D1. So for this case, if 4 electrons are released, then it will get 4F0 configuration, that is basically the xenon configuration, that is the inert gas like configuration, right? Next question, what is the highest oxidation state shown by actinoids? So that's going to be neptunium and plutonium, +7 oxidation state it shows. Okay, let's go ahead. How is potassium permanganate is manufactured? I guess I don't have to tell, multiple times this question came, and most important thing, okay, and please remember the balanced chemical equation for this case. Okay, let's go ahead. Potassium dichromate, this is also very important question for both of the cases. Let me write, this is also very important, this is also going to be very important. Okay, you can't leave this question, balanced chemical equation, multiple times you write, sometimes in the form of fill in the blanks also they keep asking this type of question. Okay, let's go ahead. What is lanthanide contraction? Next, what is the cause of lanthanide contraction? Okay, one by one we can go ahead. That is a gradual decrease in the atomic and ionic radii from lanthanum to lutetium, that is called the lanthanide contraction. What is the reason? Reason is basically poor shielding of d and f orbital, right? Next, any two consequences you can take, that gradual decrease in atomic radii. Okay, you will see the similar properties in the 3D and 4D, right? So 4D and 5D basically. So zirconium and hafnium, almost same. They're basically very difficult to separate them from their ore. Okay, next is basicity decreases from lanthanum to lutetium. That is also one of the example you can take. Okay, let's go ahead. Study the actinide elements is difficult. Give 3 reasons. So it's a very important question. So first of all, this is radioactive. Handling radioactive elements are very tricky. Next, half-life is very short, means they exist, they become stable for a very short period of time, only 3 minutes, like that. Next, they could be prepared in nanograms. Nanograms is very small amount they can be prepared. So while working with them, you need more amount of that particular thing, right? But if you get it in small amount, how you should proceed the studies? So that is the reason. Let's go ahead. Lanthanoids and actinoids difference. You can see any 2 or 3 you can just pick and you can just go ahead. Next, why chromium 2 plus is reducing and Mn3 plus is oxidizing. So for this type of question, what happens, you can just go ahead with the what it calls the electronic configuration. Okay, so if you see chromium, if chromium is reducing, then the electronic configuration will be D4 to D3. Okay, D3 means half filled T2G, because T2G can have, like, if T2G becomes half filled, it will be 3 electron, it will carry 3 electron, right? So D3 means half filled T2G, that will give you some stability, that will give it some stability. Next, if you just look for the Mn3 plus will get a D5. So D5 is half filled entire d orbital, that will give some extra stability. Okay, so D5 configuration has some extra stability than that of the D3. Okay, I guess this is clear. Next, why is the highest oxidation state of metal exhibit in its oxide or fluoride? Okay, so both oxygen and fluorine, they are very electronegative and smaller in size. Okay, because of this thing, manganese, vanadium, okay, they form their higher oxidation compound with manganese and fluorine only. Okay, next question, you can see which is a stronger reducing agent between Cr2 plus and Fe2 plus and why. Okay, so just again for this type of question, again just look for the configuration. So Cr2 plus, if you just check, it changes from D4 to D3, right, as a reducing part. Okay, so D3 is stable. Why? Because half filled T2G, right? So that's the reason Cr2 plus is a stronger reducing agent. I guess it is clear. Let's go ahead. Why do transition metal exhibit higher enthalpies of atomization? Okay, so higher enthalpies of atomization, it arises because of the presence of unpaired electron in it. Okay, so whenever unpaired electron is present, they have very strong interionic interaction, interatomic interaction. So interatomic interaction, if it is more, then you need more energy to break the interaction in between two atoms. Hence, you can say that enthalpy of atomization will be more. Okay, next, enthalpy of atomization is maximum in the middle of the transition series. Why? Because the number of unpaired electron is more in the middle of the series. Okay, so next question, you can see in the series scandium to zinc, the enthalpy of atomization of zinc is lowest. Why? Because zinc is having no unpaired electron at all, right? It has no unpaired electron, so enthalpy of atomization is least. Next, enthalpy of atomization is more in 4D and 5D series than that of the 3D series. Okay, this is why, because of the, again, strong metal-metal bond, because of the heavy transition metal. Okay, they have stronger metal-metal bond than compared to that of the 3D, right? I guess this is clear. Next, okay, here we are entering into the haloalkanes and haloarenes chapter. Okay, so let's go ahead with the haloalkanes and haloarenes chapter. So here comes the first, you can see Swartz reaction, Finkelstein, Woods reaction, Fittig reaction, Woods, Fittig and Sandmeyer. So these name reactions you have to remember for this particular chapter. Direct questions comes out of it. Okay, so one by one you can see this is the Schwarz reaction, just a small recap for you people. Okay, so in presence of silver fluoride or any kind of metal fluoride like mercurous fluoride or COF2, for this type of case bromine will be replaced with fluorine. Okay, so alkyl fluoride in order to prepare. Okay, so next this is basically the Finkelstein reaction. So Finkelstein reaction, basically alkyl iodides are often prepared, okay, from the alkyl bromide. So same reaction, if I just write it for you, CH3Br, if you are having, what do you have to give? Sodium iodide NaI in dry acetone. Okay, so you will end up with CH3I. Okay, so I guess this is clear. Okay, one more, this is NaBr, this is basically the byproduct. Okay, I guess this is clear. Let's go ahead. So this is basically the Fittig's reaction. Aryl halides when treated with sodium in dry ether give compound where two aryl groups are joined together. So this is the reaction, you can see aryl halide in presence of sodium in dry ether, they will form diphenyl. Okay, so now you can see okay, Sandmeyer's reaction if I go ahead with, then the aniline reacts with dilute nitrous acid. Just let me show you the reaction. So if you are having aniline, okay, you can go ahead with the diazotization NaNO2 plus HCl. Okay, or directly you can write HNO2, better to write that. That is HNO2, right? That is the nitrous acid. Okay, HNO2 0 to 5 degrees Celsius. Okay, so you will get benzene diazonium chloride N2 plus Cl minus, right? For this case, if you further give Cu2Cl2, then you will end up with Cl. Okay, this is basically the Sandmeyer's reaction. I guess this is clear to you. Let's go ahead. Give the preparation of aryl halides by Sandmeyer's reaction. So again the same thing I already discussed with you. Okay, so for this case you have to complete the reaction. Let's go ahead. So for this case, whenever you are using KNO2, you will end up with CH3ONO. Okay, now for this case, in presence of sodium in dry ether, you will get the Fittig reaction, right? So two benzyl unit will be attached like this. Okay, I guess this is clear to you. Let's go ahead. Saidzev rule. Okay, Saidzev rule, let me just explain with an example. So, okay, let me just write down this statement for this. So, let's say dehydrohalogenation is taking place. So, during dehydrohalogenation, more substituted alkene alkene will be the major product. Okay, so let me just give you one example. So let's say I am having the compound CH3, let's say CH, here I have one hydrogen, here I am having CH, here Cl, here I am having CH2, here I am having another hydrogen. So it has two options to go through dehydrohalogenation or beta elimination. One is this particular hydrogen can jump, this chlorine can come out. Okay, another one is this can jump and this can come out. So for the first case, if I go ahead, I will get it like this: CH3, CH, double bond, CH, CH3, right? For the second case, if I go ahead, I will get it something CH3, CH2, CH, double bond CH2. Okay, so for this case, here you can see this particular alkene is more substituted, right? This is more substituted. Okay, so that's why this is going to be the major product. Okay, I guess this is clear for you. Let's go ahead. Aryl halides are less reactive towards nucleophilic substitution. Why? Because of the resonance effect and sp2 hybridization also you can take it. Okay, so resonance effect, what happens? See, if you are having aryl halide, means this type of compound. Okay, so what happens if you want to do nucleophilic substitution? So this particular thing should be substituted. Okay, now if this particular bond is very much stable because of resonance, then how you will remove this, right? It has some partially double bond character. Okay, it has some partial double bond character. Okay, so basically what happens, you can see, if you are having Cl has lone pair, it can jump here, it can go there. So here for this particular bond, you will get some partial double bond character while doing the resonance, right? Next one is sp2 hybridization of carbon. So sp2 hybridization gives some more S character, right? And the bond becomes very strong. Okay, the bond like the carbon and chlorine, basically they holds very strongly to each other. Okay, I guess it's clear. Let's go ahead. Write the steps involved in SN2 mechanism for the conversion of chloromethane to methanol. Okay, so SN2 reaction, right? So let's go ahead. Carbon, here let's say I'm having chlorine, here let's say I'm having hydrogen, here another hydrogen, here I'm having one more hydrogen. Fine, so this is my chloromethane. So SN2 reaction is a single step reaction, single step concerted mechanism. It goes through a transition state, penta coordinated transition state. So if you like here you can see if you give OH minus, okay, so what it will do, it will attack from the back side to the carbon, okay, and it will form a penta coordinated transition state. This is the transition state. Okay, after that what happens, this chlorine leaves the system, okay, and you will end up with a structure like this. Okay, so once you just notice properly, you can see a tilted structure you will get. Okay, so if you start with a chiral atom, if you start with a chiral carbon, okay, you will end up with the inversion in configuration. Okay, after SN2 reaction. I guess this is clear to you. Let's go ahead. Okay, what are freons? Name the poisonous gas evolved when Cl2 is oxidized by air. Okay, one more thing, just this is a very, very important question. Don't skip it, okay. So here you can see the chlorofluorocarbon compounds of methane and ethane, they are called as freons, okay. And the gas that evolved after oxidation, it is called basically phosgene, okay. Go ahead. Physical properties, the question comes like in haloarenes, para isomers have higher melting point as compared to ortho and meta. Why? Because para isomer is more symmetrical, hence it can fit into the crystal lattice system more properly. Okay, so let me write. The answer is basically para isomers are symmetrical. Okay, hence they can fit into the crystal lattice nicely. Next, arrange the increasing order of the boiling point. Okay, so first see here you can see bromo and chloro compounds are there. Okay, bromine is having maximum like more atomic weight than that of the chlorine. So here you can see if I just mark them, let it be my 1, let it be my 2, let it be my 3, let it be my 4. Okay, so 1, 2, 3, 4 if I marked. So dibromomethane, here I am having 2 bromine. Bromomethane, bromoform. Bromoform, if you see, the bromoform looks like this. CHBr3 means it is having maximum number of bromine, right? So for this 2 will be maximum. After that dibromo, right? Dibromo compound. After that bromomethane. After that chloromethane. Okay, I guess this is clear. Let's go ahead. 1 chloropropane, isopropyl chloride and 1 chlorobutane. Okay. Okay, let me just number them again. This is my 1, this is my 2, this is my 3. Okay, butane means the chain length is maximum, right? So 3 will be maximum. After that if you go through 1 chloropropane, because it is a chain like structure. A little bit branch arises in isopropyl chloride, so after that it will be 2. I guess this is also clear to you. Let's go ahead. Chloroform is stored in closed dark colored bottles. Why? Because it's slowly oxidized by air in the presence of light, okay, and it forms the poisonous gas phosgene. Okay, to avoid this we can use a dark colored bottles. Okay, let's go ahead. Write any 3 differences between SN1 and SN2 reaction. Here you can see the reaction, you can, I mean the differences you can go through from here. Next, identify the A and B. Okay, for the first case, let me just write the A. A is going to be diazonium chloride, N2 plus Cl minus, and B, it is basically the Sand-Meyer's reaction. The reagent is, you can use Cu2Br2. Okay, I guess this is all good. Let's go ahead. Okay, so let's go ahead with the next question. Write the mechanism involved in the conversion of 2-bromo 2-methyl-propane to 2-methyl-propan-2-ol. Okay, let's draw the structure. So CH3, C, CH3, here CH3, here Br. Okay, so first what I have to do, so this is basically SN1 mechanism. Okay, because from here you have to come up with this structure. CH3. You have to come up with this structure. So definitely it's going to be an SN1 reaction mechanism that you have to follow. Okay, so the first step, if I just go ahead with step 1 is basically the formation of carbocation, right? So here what happens? The leaving group leaves the system. So this will leave the system and the step is going to be slow. Hence you can call it the rate determining step, and it will give you the carbocation, right? Okay, next we can go ahead with the step 2. Step 2 is basically the nucleophilic attack. Okay, so here we can use the OH minus. So now I am having the carbocation like this, CH3, CH3, here CH3, here I am having OH minus, this will attack here, and as a result of this you will get your desired product. Okay, OH. Okay, this particular step is going to be fast. I guess this is clear. Yes, this is the entire SN1 mechanism. Okay, next you can see which type of solvent favors this type of reaction. See, here carbocation as an intermediate you are getting, right? So if you can stabilize this intermediate, If you can stabilize this carbocation intermediate, then your reaction will be faster. So as a result of this, you can use polar protic solvent. Okay, because it is a charged intermediate and hence you need a polar solvent, okay, to stabilize it. Next, define enantiomers, and next is racemic mixture. Okay, so here you can see this is the enantiomer definition, the stereoisomers that is related to each other as a non-superimposable mirror image. Okay, next, racemic mixture. So a mixture containing two enantiomers in equal amount, so the optical activity gets cancelled out. Okay, so this is called racemic mixture or racemic modification sometimes. I guess it's clear. Let's go ahead. Okay, one 5-marker question. Okay, so for this type of problems, just write an overview of what they are saying. So first they are saying a primary alkyl halide C4H9, that is A, reacted with alcoholic KOH to give you compound B. Fine. So what they are saying, I am having C4H9 beer, right? It is on being treated with alcoholic KOH. It is giving me B, right? Compound B reacted with HBr gives C. So it is reacting with HBr, it is giving you C. Fine. Okay, which is an isomer of A. So C and A, this is my A, right? C and A, they are basically isomer. Okay. When A reacted with sodium metal, it gives compound D. Okay. When A reacts with sodium metal, it gives compound D with the formula you can see C8H18. Okay. This is my D, which is different from compound formed when N-butyl bromide is reacted with sodium. Give the structural formula of A. Fine. So how I should get the structural formula of A? That is N-butyl bromide treated with sodium. So N-butyl bromide, let's start with. So N-butyl bromide, CH, here CH3, here CH3, right? CH2 beer. This is my N-butyl bromide, right? So that's going to be my A. Fine. So now treat this with alcoholic KOH. Treat this with alcoholic KOH. So it will undergo dehydrohalogenation, right? So if it undergoes dehydrohalogenation, you will get the compound something like C double bond CH2, here CH3, here CH3. Okay. Further, if you give HBr, it will undergo Markovnikov mechanism, right? So you will get something C, here CH3, here Br, here another CH3, here CH3. Okay. So this is your A, this is your B, okay, this is your C. Let's write D as well from here. So sodium metal if you treat, okay, it will undergo Woods reaction, right? So this two structure will be attached to each other. CH, CH3, CH3, CH2, another CH2. This 2 unit of this molecule will be attached to each other. CH2, CH, here CH3, here also CH3. Okay, this is your D. Okay, I guess this is clear to you. Okay, so yeah, let's go ahead. You can see A and C, they are isomers of each other as well. Okay, let's go ahead. Okay, now we are going to discuss about the alcohol, phenols and ethers. Okay, so preparation of phenol from cumin, it's a very important reaction. So this is the thing, cumin, the isopropyl benzene. Sometimes they ask what is the IUPAC name of cumin. You can write isopropyl benzene. Okay, cumin hydroperoxide in presence of H plus, it will give you phenol. Along with that, you will get acetone. That is also important. In the MCQ, this question comes. Williamson ether synthesis, alkyl halide on heating with alkoxide in alcoholic medium gives ethers. Let me show you the reaction. Let's say I am having let's say CH3, CH2, O minus, Na plus. This is an alkoxide. Okay, let's say I am having CH3Br here. Okay, it will undergo SN2 type of mechanism. Okay, and this alkoxide will attack here and this Br will leave. Okay, and you will end up with one ether, that is CH3, CH3, CH2, O, CH3 plus NaBr. Okay, this is the Williamson ether synthesis. I guess it is clear. Let's go ahead. Okay, convert the following reaction. Okay, so for the first case here you can see it is a okay. For the next question here you can see it is a 2-degree alcohol, right? So for this case you will get a ketone. So for the first case your answer is going to be acetone. Okay, for this case you will get C6H5 means this is a phenol basically. Phenol in presence of zinc dust, it will give you the benzene. Okay, I guess this is clear. Let's go ahead. Okay, identify A and B. Okay, so identify A, you know this reaction very clearly. This is going to be salicylic acid, OH, and here COOH. Okay, for the next case, this is basically ether in presence of HI. So okay, one alcohol you will get and one alkyl iodide you will get. So the iodide compound that you will get is something like this, CH3, CH3, CH3. Okay, this is your B. Along with that, the alcohol you will get. Okay, so let's go ahead. What is Lucas reagent? How would you distinguish between 1 degree, 2 degree and 3 degree alcohols by Lucas reagent? Okay, okay. So Lucas reagent is basically the mixture of ZnCl2 and HCl. Okay, so now how will you distinguish? You can see it basically follows the SN1 path. Okay, so if you are having 3 degree alcohol, let's say CH3 whole thrice COH, this is a 3 degree alcohol, right? Okay, if you just treat this with ZnCl2 in HCl, it will form CH3 whole thrice CCl immediately. Why? Because the carbocation is very much stable here, right? It will form immediately. So you will see immediate turbidity. Okay, next if you start with a 2 degree system, CH3 whole twice CHOH. Okay, same reagent I am going through. You will get the turbidity of CH3 whole twice CH, here you will get Cl. So you will get the turbidity after 3 to 5 minutes after. Okay, next if you go ahead with the 1 degree one, sorry, if you go ahead with 1 degree alcohol, okay, so that is basically CH3 CH2 OH. For this case same reagent, so for this case no reaction. Okay, in case if you heat you will get some turbidity, but in room temperature no reaction. Okay, I guess this is clear to you. Let's go ahead. Boiling point of alcohols are higher than that of the other class of organic compounds. Okay, next alcohols are soluble in water. Only one reason, that is the hydrogen bonding. Okay, alcohol and alcohol, they can form intermolecular hydrogen bonding with each other. So to break that, you need more temperature, hence boiling point increases. Next, soluble in water, because alcohol can form hydrogen bond with the water molecule, that's why they become soluble. Next, what are rectified spirit, what is absolute alcohol, and what is denatured alcohol? So rectified spirit, there is a ratio 95.5% ethanol and 4.5% H2. They form azeotropic mixture in this particular composition. Next, absolute alcohol is 100% pure ETOH, ethanol. Okay. Next, denatured alcohol means commercial alcohol, they made unfit for the drinking purpose by mixing CuSO4 for the coloration and pyridine for the bad smell, okay, and sometimes methanol. So this particular phenomenon is called denaturation. Among the orthonitrophenol and phenol, which is having the higher pK value? Okay, so basically we know that orthonitrophenol will be having intramolecular hydrogen bonding, right? So that will stabilize the system. But what happens, as I am having NO2 group, NO2 being highly electron, NO2 is having highly electron withdrawing in nature. Here I am having OH. So I am having both minus I and minus M effect or minus R effect. Okay, so that will compensate the hydrogen bonding. Okay, so this will overcome the hydrogen bonding, and hence the oxygen hydrogen bond will be breaking quickly. Okay, so this will be more acidic in nature because the phenoxide ion that you will get out after it, okay, orthonitrophenoxide ion, that basically will get stabilized through resonance. Okay, that will actually overcome the hydrogen bonding effect. Okay, so acidity will be high for this case. Acidity will be high, hence pKa will be less. So definitely for the phenol, acidity will be less, hence pKa will be more. Okay, I guess this is clear for you. Let's go ahead with the problem next. Okay, how do you prepare aspirin from salicylic acid? So basically you have to treat the salicylic acid with acetic anhydride. Okay, so acetic anhydride will give you the acetyl salicylic acid or aspirin. The formula, the IUPAC nomenclature for this is 2-acetoxybenzoic acid. Let's go ahead. Orthonitrophenol is steam volatile but not paranitrophenol. Why? Because orthonitrophenol is having intramolecular hydrogen bonding. So here you can see I am having OH, this N, O minus, this. Okay, so they are having the intramolecular hydrogen bonding, but paranitrophenol is having intermolecular hydrogen bonding, right? So that's the reason this is steam volatile, but paranitrophenol is not. It has boiling point, okay, higher boiling point. How to separate? We can use the steam distillation method. Okay, let's go ahead. Coles reaction. Coles reaction, I guess you know, you have to treat this with CO2. Okay, after phenol being treated with NaOH, it will form the phenoxide, then CO2 if you treat, you will get salicylic acid. Okay, let's go ahead. What is the Dimet-Heman reaction? Very important, both of them basically. If phenol is treated with chloroform and NaOH, you will end up with the salicylaldehyde. Okay, let's go ahead. What happens when diethyl ether is heated with limited amount of HI and excess amount of HI? Okay, so diethyl ether means CH3, CH2O, CH2, CH3. Okay, so once it will form the alcohol, another case it will form the iodide. Okay, so if it is treated with HI, first limited HI, this is number 1. Okay, so you will end up with CH3, CH2, OH plus CH3, CH2I, right? Now if you give excess HI, then this particular alcohol will also get converted to iodine. So this CH3, CH2, OH further will react with excess HI, it will give you CH3 CH2I. Okay, I guess this is clear to you. Okay, explain the mechanism of the dehydration of ethanol to ethene. So this is the mechanism. First, protonation of the alcohol, then carbocation formation by leaving this leaving group, OH2 plus will be leaving the system and it will give you the carbocation, then that elimination of a proton, that will give you the double bond. Okay, very important question. Okay, identify A and B. So for this case, let me tell you what is A. A is going to be salicylic acid, it's going to be OH and here COOH. Okay, so for this question I already solved this. Here B is going to be tertiary butyl iodide. Okay, I guess this is clear to you. Let's go ahead. Okay, so identify A in the following reaction. So phenol, if it is treated with excess, I mean bromine water, okay fine, bromine water if it is treated, then all the ortho and para position will be substituted with the bromine. Okay, now phenol is treated with zinc dust, you will get the benzene ring. Okay, now for this case CH2 C2H5OH, if it is treated with Na, then you will end up with hydrogen gas. That's it. Okay, so I guess this is clear. Next, how do you prepare phenol from the aniline? So what you can do is, from the phenol you can just from the aniline you can just diazotize it. So you will get diazonium chloride, just treat it with water, you will get your phenol. Okay, this is the thing. You can treat it with NaNO2 plus HCl, Na2Cl minus will be formed over here. Water, warm it, you will get your phenol. Okay, let's go ahead. Explain the mechanism of dehydration of alcohol to ether. So this is a mechanism. You can see protonation of alcohol is the first step, then SN2 attack. Okay, SN2 attack, after this just elimination of proton will give you the ether. Okay, how anisole react with acetyl chloride? So that's going to be Friedel-Crafts acylation reaction. This thing, if you just treat anisole with CH3COL, CH3COCl in presence of anhydrous AlCl3, you will get 2-methoxy acetophenone and 4-methoxy acetophenone. That's going to be the major one. Let's go ahead. Okay, explain the mechanism of hydration of alkenes to alcohol. So this is the mechanism. You can see alkene at first it will attack on the protonated water. Okay, protonated water, and it will form the carbocation. Next, carbocation will be attacked by water, nucleophilic attack, right? You will get protonated alcohol over there. Now water will takes one hydrogen from this and you will end up with the alcohol. That is a mechanism. So, okay, so next you can see complete the following reaction. Okay, let's go ahead with this. So the first thing they are saying is CH3, wait just a minute, CH3 CH double bond CH2. So here I have to add H2O in presence of H plus. Okay, so I will get alcohol out of it. So CH3, here I will get OH, here I will get CH3, this is CH, here I will get CH3, right? Next, for this system, if I treat this with CrO3, CrO3, it will oxidize it, I will end up with the ketone, CH3, C double bond O, CH3. Okay, so complete the following reaction. So that's it. So I guess this is clear. This is your propan to all, and this is going to be propanon. Okay, I guess this is clear. Let's go ahead. Okay, this type of question, an alkene X reacts with H2OH plus to give you compound Y. Okay, so one by one we will go ahead with this. Okay, let's go ahead with the problem. An alkene X C3H6 reacts with H2OH plus to give you compound Y. Fine. So if you want to prepare one alkene using this 3 carbon and 6 hydrogen, only one possibility is there. That is, you can make CH3 CH double bond CH2. This is the only possibility. Okay, so this is your X, right? Now you are treating this with H2O in presence of H plus. It is simple and it is similar to that of the previous problem. You can see H2O and H plus will give you one alcohol. CH3, right? This is your Y. This undergo reaction with CrO3 H2SO4 to produce Z. Okay, it is quite similar. CrO3, if you treat this, you will end up with the acetone. Okay, so write the IUPAC name. Okay, so this is going to be propene. Okay, this is going to be propantool. Okay, and this is going to be propanone. This is your Z, right? This is your propanone. Okay, which among the following compounds have lowest and highest pK value for paranitrophenol? Okay, let's name them. Paranitrophenol, let it be A, phenol B, ethanol C, and orthocresol, let it be D. Okay, so paranitrophenol, it looks something like this. Here I am having NO2, right? Here I am having OH. Okay, next I am having phenol, OH. Next I am having ethanol, CH3, CH2, OH. Okay, next I am having orthocresol. So here I am having phenol, in the ortho position I am having CH3. Okay, so here you can see for this case I am having electron withdrawing group. Okay, so acidity for this case is maximum. So A comes maximum, acidity order if I write. After that, which one will come? After that you can take it as phenol, right? After that you can take it as phenol. Okay, after that you can take it as normal A, B, C. This you can take as C, and this particular group is electron donating group. Electron donating group. As a result of this, the acidity will be less. So then it comes D. So definitely from here you can see, wait, but here I am having one benzene ring. So for this case you can just go ahead with at first C, at first D will come, then you can go ahead with C. Okay, at first D will come because here you are having one benzene ring to stabilize the phenoxide ion, right? So D will come, then this is C. Okay, so from this thing you can tell that paranitrophenol, that is option A, they are having acidity high, hence pKa less, and your C, that is ethanol, acidity is less, hence pKa is high. Okay, I guess this is clear to you. Okay, let's go ahead. How is phenol prepared from the benzene sulfonic acid? Write the equation. So this is simple. In benzene sulfonic acid you can treat this with NaOH. Okay, how anisole reacts with methyl chloride? So that is basically Friedel-Crafts mechanism. You can see Friedel-Crafts alkylation. Okay, so next, what is the effect of electron donating group on acidity? So electron donating group means acidity will decrease. Okay, I guess this is clear. let's go ahead. Okay, so here we are going to start with the aldehydes. Okay, give the IUPAC name of these compounds. So first case, let me just tell you, you can call it ethanol. Okay, next one you can call it as prop, because three carbon system, 1, 2, 3, right? So prop, in the 2 position I am having double bond, 2 enol, right? Prop 2 enol. Okay, for this case, this is basically one ester type of compound, right? So you can see ethyl ethanoate. Okay, you can go ahead with ethyl ethanoate. I guess this is clear. Next, explain Getterman-Koch reaction. So this is the reaction for the benzene. If you just treat this with carbon monoxide in HCl, you will get it CHO. Okay, so write the equation for the reaction between carboxylic acid and PCl5. Okay, so let me just go ahead. See, this is carboxylic acid. In presence of PCl5, it will give you acyl chloride type of compound. Okay. Okay, next question, you can see the reaction between formaldehyde and concentrated KOH. Okay, so formaldehyde and concentrated KOH, if I go ahead, then I will get Cannizzaro product, because it has no enolizable hydrogen, plus KOH. So if I go through, then I will get COO, here hydrogen, here O minus, K plus CH2OH. Okay, so this is basically Cannizzaro reaction. Okay, next, the formation of oxime from the carbonyl compound. Okay, so oxime, you can take carbonyl compound and you can take hydroxylamine, NH2OH. As a result of this oxygen and this hydrogen, they gets released in the form of water, and you will end up with this. Okay, I guess this is clear to you. Let's go ahead with the next question. Among formic acid and acetic acid, which is more acidic? So basically formic acid is more acidic because the conjugate base is more stable than that of the acetate ion. Okay, let's go ahead. Explain the preparation of carboxylic acid from the Grignard reagent. So you have to just treat this with carbon dioxide. Okay, so let me give you one example. HVZ reaction example is already given. You can see any carboxylic acid, if you wanna do the alpha halo substituted acid, if you wanna get, then you can treat this with any kind of Cl2 or Br2 in presence of red phosphorus. So alpha halo substituted carboxylic acid you will end up with. Okay, so let me just give one example with the carboxylic acid preparation. Let's say I am having CH3MgBr. Let's say I am having CH3MgBr. I am treating this with dry ice, means carbon dioxide. So this CH3, this is delta negative, this will attack here, this bond will open up, right? So you will end up something like C double bond O, here CH3, here OMgBr. Next, if you just hydrolyze it, means if you just treat this with H3O plus, then you will end up with C double bond O, here you will end up with OH, and here you will get CH3. So here you can see one acetic acid or carboxylic acid is formed. Okay, I guess this is clear. Let's go ahead, write the general equation involved in the addition of ammonia and its derivatives to the carbonyl group. So this is the ammonia derivative. You can see once it will attack in the carbonyl carbon, you will get a tetrahedral intermediate and you will end up with this. Okay. Explain Cannizzaro's reaction with one example. So aromatic aldehyde, it undergoes Cannizzaro reaction due to the absence of alpha hydrogen. So if I just write this CHO in presence of let's say NaOH, concentrated NaOH, if I just take, then you will end up with COO minus Na plus, along with that CH2OH, benzyl alcohol you will end up. This is Cannizzaro reaction. Okay, so I guess this is clear. See, aromatic aldehydes do not answer Felling's solution test. Okay, why? Because of the absence of alpha hydrogen, it will not undergo Felling's test. It will undergo Cannizzaro reaction instead. Okay, let's go ahead. Okay, so here you can see with respect to structure of carbonyl group, give the following. First, hybridization of carbonyl carbon, that is going to be sp2, sigma and pi bonds. So how many sigma bond? 3 sigma bond and 1 pi bond in between carbon and oxygen. Geometry, it's basically trigonal planar and 120-degree bond angle. Explain the conversion of toluene to benzaldehyde. So this is using the side chain chlorination. Okay, so side chain chlorination means you just have to go ahead with the chlorination at first. It will form benzyl chloride, from there benzaldehyde. Okay, go through the question properly, don't rush. Okay, otherwise from the toluene you can directly go ahead with the ATAD reaction as well. Don't do that. They are asking for the side chain chlorination, you have to go with this method only. Let's go ahead. Okay, let's go ahead with the next problem. Butane, okay, write the chemical reaction to affect the following transformation. Okay, so butane 1 all, if I just write, that is CH3, CH2, 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 OH. Okay, so from here you have to come up with butanoic acid, right? CH3, CH2, CH2, COOH. Okay, so just simple add KMNO4. Next, cyclohexene to cyclohexane 1,6-dioic acid. For this case also you can go ahead with the KMNO4. So cyclohexane, just one double bond, any one position I am giving. Okay, so now from here they are asking to give you, let's say this is my position 1, 2, 3, 4, 5, 6. Okay, so 1,6-dioic acid. So let's take the double bond here. Okay, so you will get COOH and COOH. Okay, so here you have to give again KMNO4. Right? Clemenson reduction. Here you can see the example. If you are having carbonyl, zinc amalgam in presence of HCl, it will give you this hydrocarbon. Let's go ahead. Okay, so butanal to butanoic acid. So butanal to butanoic acid, you can just go ahead with the Tollens reagent. Okay, I am not showing you, I am just writing the reagent. Okay, so I guess it is clear to you. Let's go ahead. Okay, explain the test to distinguish between aldehydes and ketones. So basically, to distinguish between aldehydes and ketones, simply we can use the Tollens reagent. Okay, so it will give you the silver mirror precipitation, right? Next, you can see, complete the following reaction. Okay, so this is Friedel-Crafts acylation reaction, right? So you will get things something like that. This thing you will get. Okay, so this is again oxime formation you will end up with. C here CH3, here CH3, here double bond N OH. Okay, this is the oxime formation. Okay, I guess this is clear to you. Okay, next, among 4 nitrobenzoic acid and 4 methoxybenzoic acid, which one is more acidic? So definitely it's going to be 4 nitrobenzoic acid is going to be more acidic because of the presence of electron withdrawing group. This is going to be more acidic. Okay, earlier also we did this type of problem. Let's go ahead. Okay, I guess this is the reason it's written over here. Let's go ahead. Okay, so you have to write down the product here, X, Y and Z. Fine. Let's write. For this case, we can write, here I am having NO2 group, okay, MgBr, okay. So now if you treat this with dry ether, dry ice, that is CO2, so definitely you will end up with carboxylic acid, okay. So this is going to be here NO2, here COO minus MgBr. Now Z, if you just simply do hydrolysis, so you will get meta-nitrobenzoic acid. Here you are having nitro group, this will be your carboxylic acid, okay, as simple as that. Okay, arrange the following aromatic carboxylic acid, the increasing order of their acidity. So here you can see, if I just number it as 1, if I number it as 2, if I number it as 3. So this is electron withdrawing group. This is electron donating group, okay. Electron withdrawing group will increase the acidity, so 2 will come first, after that 1 will come, then 3. I guess it is clear to you. Let's go ahead. Okay, what is haloform reaction? Give an example. What is aldol? Okay, one by one, let's go ahead. Haloform reaction is if you are having methyl ketone unit in your system, then it will be oxidized by sodium hypochlorite or hypohalite type of thing. Okay, so if you are using sodium hypoiodide, NaOI, then you will end up with the iodoform test. You will end up with the yellow colored precipitation. Okay, so that is the haloform test. Here you can see one example is also given. So what is aldol condensation? Give an example. Here comes aldol condensation. The aldehydes ketone, they are if they are having the alpha hydrogen, they will undergo self condensation in presence of dilute alkali. Okay, they will give you the beta hydroxy aldehyde type of thing. Further on being heated, they will give you alpha beta unsaturated aldehydic unit. Okay, let's go ahead. Name the product formed when formaldehyde undergoes Clemenson reduction. So see, if this particular thing, if it undergoes if this particular thing, formaldehyde undergoes Clemenson reduction, okay, then you will end up with the methanol. Okay, not hydrocarbon. Let's go ahead. Okay, so complete the following reaction. Okay, so here you will you can see Grignard reagent is treated with dry ice, so you will end up with carboxylic acid, CH3COOH. Okay, next CH3COH in presence of SOCl2, so you will end up with CH3COCl. Okay, next one, you will end up with amide, CH3CONH2. Okay, I guess this is clear to you. Okay, let's go ahead with the next problem. What is haloform reaction? Give an example. So here you can see, if your compound is having one methyl keto unit, then it will undergo like it will give you the haloform test, okay, in presence of sodium. Okay, sodium hypohalite. Okay, so if you are using sodium hypoiodide, then basically you will end up with the iodoform, that will give you the yellow precipitate. Okay, next, what is aldol condensation reaction? So if you are having alpha hydrogen with respect to the carbonyl, maybe it is aldehyde, maybe it is ketone, it will undergo self condensation reaction in presence of dilute alkali. Okay, so you will get beta hydroxyaldehyde or ketone type of system, and on being further heated, you will end up with the alpha beta unsaturated carbonyl. Okay, so that is the aldol condensation. Next, you can see, name the product formed when formaldehyde undergoes Clemenson reduction. Okay, so wait, let me tell you, this is not going to be methanol. So basically, if you are having this type of unit, then if you treat this with Clemenson reduction, means ZnHgHCl, then you will end up with hydrocarbon, means CH4 here you will get. Okay, so you will get methane out of it. I guess it is clear. Let's go ahead. Okay, let's go ahead with the next question. Okay, first this will give you the acetic acid. Next this will give you CH3COCl. Okay, next this will give you amide. Okay, I guess it's clear. Next question, the pK value of acetic acid, benzoic acid and trifluoroacetic acids are given like this. Arrange them in the increasing order of their acidic strength. Okay, so they are asking for the acetic acid, that's it, that's CH3COOH, benzoic acid, this one, and then trifluoroacetic acid, right? So I am having CF3COOH. Okay, so that's going to be maximum acidic, after that this, after that this. Okay, because lower pKa means highest acidity. Let's go to the next problem. An organic compound X with a molecular formula C7H8O forms an orange red precipitate with 2,4-DNP reagent and gives yellow precipitate on heating iodine in presence of NaOH. So see, first here I am having a carbon more than 6, right? So we can expect one benzene ring, and it is giving a positive halo form, means it is having one methyl ketone unit, and definitely 2,4-DNP positive means definitely one ketone unit is also there. So the formula should be like this: COCH3. Okay, the formula must be like that. Now you can see it neither reduces Tollens reagent nor does decolorizes bromine water. Fine, definitely it must be ketone. On oxidation with chromic acid, X gives carboxylic acid. Okay, so if you do chromic acid oxidation, then you will end up with this carboxylic acid, benzoic acid you will end up with. Fine, this is your Ax, this is your Y. Okay, so now identify the compound X and Y, write all the reaction involved. So 2,4-DNP and NaOH reaction, let's go ahead. Okay, 2,4-DNP, if I just wanna write, so 2,4-DNP means 2,4-dinitrophenyl hydrazine, right? So NH2 NH, here I will be having in the 2 position one nitro group, in the 4 position another nitro group. Okay, so if you just go ahead with it, you will get a yellow precipitation of this compound. Here you will be having one bond with nitrogen. Wait. So these two hydrogen and these oxygen will be eliminated from the system. So C double bond N you will get here, along with that one NH, here nitro NO2, here another NO2. Okay, yellow precipitation of this particular thing you will get. Okay, I guess this is clear. Next, if I go ahead with the NaOH in presence of I2, so I will end up with definitely CHI3, I will get CHI3, that is also will give the yellow precipitation. Along with that I will get this thing, COO O minus, here Na plus will come. Okay, I guess this is clear. These are the all reaction that is involved in this particular case. Let's go ahead. Okay, between methanol and ethanol, which will undergo aldol condensation. So definitely ethanol is going to give you the aldol condensation because of the presence of what? Because of the presence of alpha hydrogen. Okay, so let's write the reaction. So CH3 COH. Okay, so what you have to give? You have to give dilute NaOH, and you will end up with the alpha beta unsaturated. I am directly writing, you will end up with the alpha beta unsaturated carbonyl. Okay, next, how do you convert propanone to propane? Okay, so propanone you can just do Clemmensen reduction. So propanone is, this is A, okay, this is B. So propanone is basically acetone, right? CH3, C double bond O, CH3. Okay, if you just treat this with zinc amalgam HCl, you will end up with propane. Okay, CH3, CH2, CH3. I guess this is clear to you. Let's go ahead, write the reaction and name the products obtained when acetophenone reacts with sodium hypochlorite. Okay, so you can see sodium acetophenone means benzene with one methyl ketone unit, right? COCH3. Okay, one methyl ketone unit is there, so it will undergo haloform reaction. Okay, so I2 in presence of NaOH, so definitely you will get iodoform, you will end up with one iodoform, that is CHI3, okay, plus this is yellow precipitation you will get, along with that you will get benzene with COO minus Na plus. Okay, I guess this is clear. Explain the formation of anhydrides from carboxylic acid with an example. So here you can see carboxylic acid, if you treat this with some reagent like H2SO4 or P2O5, then they will undergo, see, one hydrogen and one OH will be released from here and they will form the anhydride. Okay, so I guess it is clear. Let's go ahead. Okay, so let's proceed with the optional chapter that we eliminated initially. A little bit important question we will go ahead, like electrochemistry. We can proceed with the amines and biomolecules. Okay. So first we will discuss the amines. So give the preparation of para-hydroxyazobenzene. Okay, so how you should prepare this? You can see if you are having benzene diazonium chloride, along with that one phenol, then it will give you the para-hydroxybenzene. See, remember this reaction must be going on in the alkaline media. Okay, this will give you an orange dye. Okay, pKb of aniline is more than that of the methanamine. Why? Because pKb is aniline is more, means basicity of aniline is less. Basicity of aniline is less means the lone pair is less available for the donation because it takes part in the resonance, right? But whereas it is in the methanamine, methane group is there, right? So methyl group is there, right? So methyl group will be having plus I effect and it will helps the nitrogen to donate the lone pair, right? So basicity of methanamine is more, hence pKb is less. I guess it's clear. The answer is written out there. You can go through. Let's go. I guess it's clear. Next, write the general equation involved in Gabriel thalamide synthesis for the preparation of primary amine. So wait. This is the Gabriel thalamide reaction. Here you can see the thalamide in presence of KOH. Then it will form N minus. Okay, further this thing it will just react with RX. Okay, it will react with RX. Okay, so now this RX, this N minus will attack here, this X will leave the system, N will make the bond with R. Okay, further it will react with NaOH to give you the primary amine. Okay, so this is your Gabriel thalamide reaction, very important. Next question, you can see explain carbylamine reaction with equation. This is your carbylamine, primary amine in presence of chloroform and KOH. It will give you the foul smell of cyanide. Okay, arrange the following compounds in the increasing order of their basicity. So you can see CH3NH2 will come first. Okay, then it will come as NH3, then C6H5NH2. Why? Because for this case it is having some plus I effect that will help the nitrogen to donate the electron. NH3 is having no effect, but for this case nitrogen lone pair will take part in the resonance with the benzene ring, so it will come at last. Let's go ahead. What is Hindenburg reagent? How do you distinguish between 1 degree, 2 degree and 3 degree amines by using Hindenburg reagent? So basically this is the Hindenburg reagent, benzene sulfonyl chloride, okay, and you can see this benzene sulfonyl chloride, it will react with the, see this is your 1 degree amine, right, 1 degree amine, and once it will react you can see this particular compound will form, and here I am having still one acidic hydrogen, so that further can react with alkali. Hence, I will not get any turbidity when I am mixing this with alkali. So, it is soluble in alkali because it will react. Okay. Next, if you take 2 degree, if you take 2 degree amine, then already one hydrogen will react with Cl and you will get this compound. This is not soluble in alkali. Okay, this is not soluble in alkali because there is no acidic hydrogen. Okay, but further if you proceed with the tertiary amine, there is no hydrogen at all, right? There is no hydrogen to react here. So initially they will not react. Okay, I guess you understood this. Let's go ahead, explain Hofmann-Bromamide reaction. You can see if you are having CONH2 in presence of Br2 and NaOH, you will get amine, that is a 1 carbonless system. Okay, 1 degree primary amine you will get. Okay, next. Okay, let's go ahead with the problem. An aromatic compound A on treatment with aqueous ammonia and heating forms a compound B, which on heating with Br2 and KOH forms compound C of molecular formula C6H7N. Okay, C6H7N means you can just get confirmed that definitely one benzene ring is there. Okay, so write the structure and IUPAC name of A, B and C. So yeah, so if I just start with the compound, that is A means an aromatic compound A on treatment with aqueous ammonia gives compound B. Okay, so your C is going to be NH2. Your C is going to be NH2. Okay, benzene with one NH2. Okay, so now this NH2 came from some Br2 KOH. Okay, Br2 KOH. Now you have to think from which compound, if you treat Br2 KOH, you will end up with this. So definitely you must have an amide out there. Okay, so now this amide came from what? So you have to treat this with aqueous ammonia and heating, right? So NH3 on heating. So from where? From carboxylic acid. Okay, so I guess it is clear. This is going to be your A, this is going to be your B and this is your C. I guess this is clear. Okay, next give the reason during reduction of nitro compounds to amines, scrap iron and hydrochloride acids are preferred. Okay, so here comes the reason. You can see reduction with iron scrap and hydrochloric acid is preferred because FeCl2 is formed. Okay, that gets hydrolyzed, that releases hydrochloric acid during the reaction. Okay, so very small amount of hydrochloric acid we actually need to initiate the reaction. That's the reason scrap iron along with the hydrochloric acid, it is initially preferred. Okay, next you can see solubility of aliphatic primary amines decreases with increase in molar mass. Why? Because hydrophobicity increases. Hydrophobicity increases means the solubility of water, it decreases. Okay, let's go ahead. Okay, so let's proceed with the biomolecules. So direct question comes out of it. You can see what does tertiary structure of proteins represent. So basically tertiary structure of proteins, it represents the overall folding of a polypeptide. Okay, so further folding of the secondary structure gives you the tertiary structure. Okay, so definitely a very complicated huge molecular shape you will get out of it. Okay, next write a reaction to show glucose contain 5-OH group. So basically here you can see acetic acid, you have to do the acetylation of glucose, you will get the pentacetate, that can prove you the 5-OH groups are there. Next, write zwitter ion structure of glycine. Okay, so in aqueous solution, COOH group definitely it donates a proton and it will give you the like dipolar Zwitter ion. Okay, okay, it will give you the dipolar Zwitter ion. So if I just draw the structure, it will be something like C, here hydrogen, here hydrogen, here you will get COO minus, here you will get NH3 plus. Okay, I guess this is clear. Let's go ahead. Okay, what is peptide bond? How peptide bonds are present in pentapeptide? How many peptide bonds? Okay, so 4 peptide bonds are present. So peptide bond is basically these are the polymers of alpha amino acid. Okay, and they are connected each other by the peptide linkage. Okay, so these linkages, they are made out of the condensation between COOH group and NH2 group. Okay, and whenever it comes to the pentapeptides, I already told 4 peptides bonds are present. Next, write the Howard structure of maltose. So this is the maltose. You have to make the bond alpha D glucose, and alpha D glucose glycosidic linkage in between 1 and 4, carbon 1 and carbon 4. Okay, protein present in your hair, you know this, keratin. Let's go ahead. What are the reducing sugar? Give one example. So reducing sugars are those sugar that is having an open aldehydic unit to reduce the Fellings and Tollens reagent. They are reducing sugar. You can take the example of glucose, galactose, etc. Next, name naturally occurring optically inactive amino acid, that is basically the glycine. Okay, name any one vitamin that is stored in liver and adipose tissue. So any type of fat soluble vitamin, they are actually stored in your adipose tissue, that is vitamin A, D, E and K. Okay, let's go ahead. What are anomers? Give an example. Very important questions. Okay, give an example of ketose sugar. So basically what are anomers? Anomers are basically if they differ in the configuration at C1. Okay, then they are called as anomers. We can take the example of fructose. Give 3 limitation of open chain structure of glucose. It's a very important question. Okay, so basically first, if it is having one aldehydic unit, then it should also react with the skift. It should also react with the with derivative of ammonia to give you the skiff base, and also it should react with NaHSO3, but it does not react. Okay, next, pentaacetyl glucose does not react with hydroxylamine, indicating the absence of a free aldehydic group. Okay, next, D-glucose is found to exist in 2 different crystalline form, that is alpha and beta, 2 anomers. That also anomers cannot be explained using this the structures of glucose, that open chain structure of glucose. Okay, let's go ahead. Howard structure of lactose, I guess you can see that beta galactose and beta D glucose, beta D galactose and beta D glucose, 1 and 4 glycosidic linkage. Okay, what is a denaturation of protein? Give an example. Denaturation is basically losing biological activity of protein because of the change in temperature, pH, etc. So curdling of milk, okay, boiling of eggs, okay, these things you can give one examples. Next, you can see, give an example of a water soluble protein. Water soluble, give an example for a water soluble protein. Okay, okay, let's go ahead with the next question. Sorry, here the answer is given with respect to vitamin. Just a minute. Water soluble protein, you can take the example such as any kind of globular protein, they are water soluble. Okay, that is albumin. Okay, I guess this is clear. Let's go ahead. What are essential amino acid? Give example. Okay, so essential amino acids which cannot be synthesized in your body, you have to take it from outside, like lysine, valine, leucine, etc. Difference between DNA and RNA, here you can see. So one is double stranded, single stranded. Sugar is, one is deoxyribose sugar, another one is ribose sugar. Okay, next you can see, let me write it for you. Wait, for this case you will be getting deoxyribose sugar. Okay, and for this case you will get ribose sugar. Okay, for this case you will get the nitrogen base, that is AT AUGC, adenine, thymine, guanine, cytosine. For this case, you will get AUGC, adenine, uracil, guanine, cytosine. Okay, let's go ahead. What are oxidoreductase enzymes? Okay, so the enzyme that catalyzes the oxidation of any substance, okay, those are called oxidoreductase, like maltase. Next, you can see, give any one of the main natural source of vitamin K. Any kind of vegetables, leafy vegetables can be source of the vitamin K. Give reason. Sucrose is non-reducing sugar, so definitely it cannot reduce the Fehling's and Tollens reagent, right? So it has no free aldehydic unit to reduce them. That's why. Next, what is invert sugar? So basically, on being hydrolyzed, sucrose gives the glucose, dextrorotatory glucose and levorotatory fructose. But the levorotation of fructose is more than that of the dextrorotatory glucose. Okay, as a result of this, the overall configuration, it comes up to be a change, okay, to the levo, right? Sucrose itself is dextro, but after being hydrolyzed, levo is more. Levo's optical rotation is more than that of the dextro, right? As a result of this, the overall solution comes up to be levo. Okay, so that's the reason it is called invert sugar. The product is called as invert sugar. I guess it's clear. Let's go ahead. Name the storage polysaccharide present in plant. So that is basically starch. Next, name the monomer present in starch. So alpha D glucose that you can take. Next, name the components of starch, that is amylose and amylopectin. To difference, you can just go through from here. Okay, let's go ahead. Okay, so this is basically different type of disaccharides and polysaccharides. Examples of are there, and what are the monomer units, what are the linkage in between them, you can just have a revise from here. Okay, next we will go ahead with the electrochemistry. So very basic thing we can you can just go through from here just to boost up your marks further, because as I told you, like if you just go through the 6 chapters or 7 chapters that I mentioned at the beginning of the video, that can give you more than 65 plus. So these are the additional support that you can go through. Okay, so state Faraday's first law of electrolysis, write the mathematical form, and second law as well. You can see this is the first law and second law. Statement you can write. Make sure whenever you are writing the mathematical form, you are writing the abbreviation as well. Next, explain the construction standard hydrogen electrode or normal hydrogen electrode. So this is a construction of this. So you can just draw the diagram as well. So basically you are having one platinum foil out of here. Okay, this one inlet should be there from where the pure hydrogen gas should enter here. Okay, and you are having 1 molar HCl solution out of it. Okay, so once pure hydrogen gas will be passed through the inlet, then hydrogen gets absorbed on the platinum foil, right? And then this reaction will be taken place. So H plus will takes up 1 electron and it will be converted to H2. Okay, and this is the symbolic notation you can see. Okay, next explain the working principle of SHE. So I guess you can cover it from here actually. Next, platinized platinum is used for the construction of SHE. Give reason. So basically it is an inert electrode. It is used just for the absorption of hydrogen gas. That's it. Next, draw a neat and leveled diagram of H2O2 fuel cell. So this is the H2O2 fuel cell. You can see, write its anodic and cathodic reaction. In the cathode, what happens? Oxygen gets reduced to OH minus, and in anode what happens? Hydrogen gets oxidized to water. So overall reaction you can say H2 plus O2 will give you 2H2. Next, direct measurement of conductivity of ionic solution by Wheatstone bridge is not possible. Give reason. Okay, this question you can just avoid because Wheatstone bridge from that portion for a longer period of time the question did not come, but you can just once go through this. Let's go through the next question. Plot a graph of molar conductivity versus root C. Okay, root C for strong and weak electrolyte solution. For strong electrolyte, write the equation that represent the variation. So for the strong electrolyte, we have Debye-Huckel-Onsager equation. wait, we can have Debye Huckel. Debye Huckel you write, it will be enough, Debye Huckel equation. Okay, so that is basically lambda m equals to lambda m0 minus a into root c. Okay, so basically if you just plot lambda m versus root c for the strong electrolyte, okay, this is for the strong electrolyte, okay, you will get a line like this, okay, straight line. So here if you just extrapolate this, then here you will get the intercept, that intercept value is lambda m0. So this lambda m0 is called limiting molar conductivity. Limiting molar conductivity. Okay, and this is for the strong electrolyte. Okay, this is for the strong electrolyte. Okay, if you draw it for the weak electrolyte, it will be something like this. Okay, so here you can see this is for the weak electrolyte. It will not follow this equation. So for weak electrolyte, you have to measure, so definitely this not gonna touch here, wait, let me just redraw it again. Like this you will get, okay, so it should not touch the lambda m, okay, so you will not get any intercept out of here. Okay, so I guess this is clear for you. Okay, so that's it. Okay, so here comes the end. So whatever the important question that you should do or you must do for your upcoming examination, we had been covered. Okay, yes, some additional questions are also required. Okay, so this is basically a passing package. Okay, so definitely the very limited or main focused problems question I gave here. So yes, for the further information, we made different video on the physical chemistry, inorganic, organic. So please watch them to get even more MCQs, more 2-3 marker, more clarification about each and every chapters. That will be more than enough for you. Okay, so yes, if you have not subscribed, subscribe right now, give one thumbs up, and don't forget to share this video with your friends. Thank you so much for watching.